Hello. Hey there. What's up? This is see how the camera follows you.
Yeah, we noticed that at the seminar did we stay for the very good. This camera is so
Multiple participants.
I think one is fine as long as everyone can share.
So you can share all participants.
Yeah, we can share. Yeah.
Is that a setting that I would Zoom on Zoom?
I think
Because
you have to like go to your Zoom account and then go to the settings in there because I don't think you can change it from a meeting.
right.
So if you have a recurring meeting, you can set it and then all of the following meetings will be able to do that.
Because I used to have no trouble sharing it. It's been a while since I held a class over Zoom and one sound share.
Yeah. Today was the first day in 2.5 years that I got a lot. Oh yeah.
Risking it.
Oh. They really did not do it before. So I love them. And once they started adding once they started adding COVID, it was not. Hey. Yeah, they'd be terrible.
Let's see if we can get Netflix.
You can actually do place on that. Here and watch what's right now.
My mom keeps on like just like science and I don't know, it was she said she watched one episode where they used graph theory to model the Grand Central Station. Like the big clock that's in the middle is actually there to help the flow of traffic.
Oh, really?
Because essentially it ends up making a human roundabout.
Oh, I did not. Already.
So there's actual flow rather than just.
Exactly.
Probably. Absolutely.
KPLaver1.
No, not sure about the calculator.
Yeah. And the labor model and the proof is based on morale conjectures and saying like a nod to the morale conjecture, which probably is more generally interesting. Not trivial couples, but I think you'll like those.
That'd be nice to see a logical application.
Well, and it's ultra power.
Oh, it's good.
That's what we mean by couplings. Beta R minus R is not in any sense. No such thing as a coupling. It's like plane has no coupling. And in the ultra power, you get these sort of things that overlap. They have a dense linear order.
Oh.
You take their compactation, they end up complicated, they're connected.
Oh, this is the thing that you were mentioning the other day.
Yeah.
Well, thinking about beta R, thinking about beta N, which was my mind, thinking about beta R is being the same.
It's true. I mean, it's kind of complexity is caused by the connectedness. Theory is
and himself.
Just checking my email to see if you're having trouble. Were you hearing us? We're talking about.
Evening all.
Evening.
Try,
I wonder what his shirt says today.
oh yeah, what did your shirt say? Can you hear us okay?
Yeah, I can hear you.
It wants to
Can you
see
hear me okay?
Yeah, absolutely.
What's his son?
It
I'll have to
wants
make
to
a
see-
fresh cup of tea first.
Maybe when he comes back, we'll see it. This fun shirts is a Burkhart Holster. It's a YouTube channel on pathology. He always wears unmasking shirts. Yeah.
You know, once you make your audience depend on you having a new shirt every day, that gets challenging.
Yeah. He manages to do it every episode.
So can you read the shirt all right?
I like that one. You must party a lot.
Well, I guess I didn't share the emails with you guys, but when I wrote to KP and Todd asking, my subject line was, and what's in it for me? That was the subject line, and then I said that I was inviting them to give presentations. And Todd was the first one to respond. He says, "Boy, you sure know how to party now."
Yeah. Well, you asked him to talk about what did you ask to talk?
He's going to do our Warner Welcome problem under CH.
That's what it
so
was.
iterating proper coursing weeks.
Oh, because you guys wrote that paper.
So and possibly, I'm not sure. Of interest. Anybody? It's, you know, existence of Susan Tree. That also requires. Oh, no, it doesn't do the Jensen originally.
Hello.
KP. He's stepped out to the loop.
His shirt says, "I like to party and
I party and you teach
me." So that's that.
Camera moves.
Oh, really?
Wave your hand. It'll catch you.
Oh, I see.
Might have to speak.
I think it's audio.
Shut it. There you go.
There we are. All right.
And sometimes it'll zoom out and catch everybody.
Yeah.
So it's smart camera.
Yeah.
Or it's an appearance of being smart camera.
Right, it's just random.
Yeah, they actually be smart.
There you go. Zoom right in.
I saw in the news that some guy,
Has claimed that their artificial intelligence has developed full consciousness.
Yeah.
Really?
Yeah, why he's on
That's a
that.
strong claim. I'd like to see it.
Maybe I wouldn't like.
I didn't read anything more about it, but I can't tell you about it.
Have a conversation.
That's the truth.
Yeah. I feel like Turing test is very sensitive also to who's administering the test. Is this some teenager or folk? Just like, yeah, okay.
I feel like a toaster could pass the Turing test.
All right, you're on, Katie. Whenever you feel like it. See if you can share the screen. It should be set. 20 years. It's 30 years ago. He and I did this.
Oh, really?
30 years. It's funny when the Beatles came out, Sergeant Pepper. 20 years ago, I think. I went, whoa, 20 years ago.
Yeah. Yeah. Longer now.
You're on. Can you grab the screen?
Let's see if I'll, yep, I seem to be allowed to do so. Are you watching some writing paper now?
Yes.
We have a great big television screen you can all watch.
So you can see all the
Wait a minute. What? Do you see my screen or just the paper?
Just the paper, I guess.
just the paper.
Hmm. This is a situation I haven't seen before. Yeah, okay, I can write here, fine. This is another writing type program that I'm trying out right now. Okay. Maybe I'll want a black pen. Okay, there we go. Anyway, so I wrote to Alan that I was prepared. So let's talk about Stokes' theorem. Oh, wait, no, sorry. That's what I'm going to do tomorrow morning. Let's do the lever thing and such. Actually, I was, what?
Stokes didn't prove Stokes' theorem. Apparently, he just really liked to give it to people on tests.
Yeah, that's what I read too. And
Oh,
he put them on I think on the Wrangler exams, or the Tripos, if I'm not mistaken.
Yeah.
So some people attribute it to Kelvin. Any idea who actually proved it?
I don't know. I believe
Anyway, but yeah, that's what I'm doing tomorrow morning. Just to show you how versatile I am. Anyway, you wanted me to talk about cut points and lever forcing and stuff like that, and a nod to the Borel conjecture. Well, let's try. When I was preparing, I realized how much I had forgotten about the paper that we wrote together 30 years ago. So this is really old news for some people. But here's the thing. I want to talk about both problems, the cut point problem and a little bit about the Borel conjecture, because, well, surprisingly, when you prove the consistency of what we want to have in that model, you do basically the same thing in both proofs. And I want to point out the parallels. And I already mentioned to Alan that I'm not going to finish today. So on Thursday, I'll do some more stuff. Okay, so 2 problems, 1 model. And I guess the Borel conjecture is easier to state and talk about than the cut point problem. So I'm doing the difficult one first. Cut points where? Well, in beta r minus r, and not really the subcontinua thereof. But what's the thing? Well, if you take beta r, so the check-stone compactification of the real line, then you get a thing with 2 ends, sort of one of those, what do you call them? Those weights dumbbell. And we usually concentrate on the one on the right, on the positive side. We call the half line H, and we talk about beta H minus H, because that remainder is just 2 copies of that thing. And I'm not good. Pardon?
The stuff about shifts, right? Is that still open?
What?
If you, what did we talk? I'll try and think of it.
You're okay. Try again. Your voice isn't coming through very well.
We talk about order reversing subcontinuum or something.
An order reversing map. Yeah,
Yeah,
we talked about that a long time ago, and I no idea.
just ties into something that Will's been thinking about lately, but in beta n minus n rather than.
Yeah, you mean whether the shift forwards and backwards are
Yeah.
Yeah, I'm taking another crack at that one this summer.
well, good luck to you.
Yeah.
No, but yeah, the order reversing thing is also, Shala and Ilias proved that it's consistent that all automorphisms of the remainder are trivial.
Yeah.
So I guess in that
The H minus H.
Yeah.
H minus H minus beta H minus H. So I guess there you don't get to reverse anything. But I think nobody even tried under CH to do this, where you seem to have a little bit more freedom. Anyway, so where was I? Yeah. I'm not going to be working in beta R minus R really, because everything that we want to talk about can better be done in, well, the space I call M. And I'll tell you in a moment why I'm only looking at this one. Omega across the unit interval. And so we look at beta M. What does that look like? Well, okay, I have this very schematic picture in my head of that space. Here we have those unit intervals. So here 0, 1, 2, 3, and so on. They converge to that stuff at the end, and here is beta M minus M. And okay, so here we have the integers, and here is omega star, which is not really what omega star looks like, but for now it sort of looks like an interval. If you take an ultra filter on omega, then this mapping that you see here, you project everything down from omega across the unit interval onto omega. It extends to a mapping on the whole of beta M to beta omega. And then you look at all the points that get mapped to your ultra filter U here. And that is a thing that for the longest time, Alan and I have been calling I sub U. It's, well, if you call this thing I0 and you call this thing I1 and this thing I2 and so on, then to some extent I sub U is the uth term of the sequence that you're talking about. What do we know about I sub U? Well, it's connected, it's a continuum. And things that look like I sub U, they dictate basically the whole structure of the continuum beta H minus H. So if you want to do continuum theory in beta H minus H, you really do need to know these guys, because every continuum is an intersection of such things, and every continuum is a union of such things, unless it's a single point. But okay, that's the exception there. And if you, let's see if I can wake up some color. If you were to take a point in every one of those intervals, then you take the closure of those red points. You get, of course, the horizontal line of points for every one of those ultrafilters. You get a point here, and this point here, if I call this point x0, this one x1, x2, and so on, and that point I naturally call x sub u. That point is a cut point of the of that continuum. And what do we mean by cut point? Well, we have two closed sets. Okay, and I'm stretching the notation a bit. All the zeros in those unit intervals, they converge. Well, let's call it 0 sub u. That's a single point at the bottom, so to speak, of that continuum. And then there is a point at the top of that continuum that's in the closure of all the ones. And you can use the interval notation. I'll come back to that in a moment. But also, if I take so there are points, and the points in that continuum are really between 0 and 1. And the point xu divides all the points except itself into two sets. If you were to take the intersection of those two closed sets, you get just the point xu back. Now, how does that? I wrote the interval notation because there's really a limit of intervals going here to the right. The interval 0x0, 0x1, 0x2, and so on. I take the closure of that and intersect it with that piece. You do get a closed set here, and that's I denote it like so. And the same thing at the top, from x0 to 1, x1 to 1, x2 to 1, and so on. Take the closure, intersect it with I sub u, and you get a set that we denote x sub u to 1 sub u, and together they cover that very thin set over there. But if I take their intersection, then all that's left is that single point x sub u. And this is what a cut point does in a continuum. It splits the set into two disjoint pieces, two disjoint open pieces. The complement is no longer connected. There are tons of cut points in this continuum because for every choice of points in the unit interval, I get one of those points out of there, and those points do cut that continuum into two pieces. And so all those cut points they form an ultrapower of the unit interval over the ultrafilter U. You take all the sequences in the unit interval, declare two sequences to be equal if they coincide on a member of U, and that equivalence relation will give you the ultrapower there. And that's where this interval notation comes from, because that ultrapower has a linear order. And so it makes sense to talk about intervals, except that there is a twist.
Okay, question before you go on. Does the structure of that ultrapower or I sub u or any of this stuff, does it ever depend on you?
If you use a Ramsey ultrafilter or something, does that tell you
Stuff.
Okay.
yeah, all right.
There is one answer, and the other answer is there are also very many different I sub u's. If CH fails, then you can use a result of Allen's about ultrapowers of the reals to find one I sub u where you have a decreasing omega sequence of those cut points, and they bump into a very thick layer of other points.
I point out why the layers are thick.
Yeah, I'll tell you in a moment why they are thick, but I want to finish first. You can, if CH fails, you can have an omega from the top, omega 2 from the bottom gap in one ultra power. So there is an ultra filter U where you see this, and there is an ultra filter V where you see this. But in the I sub V, you don't see omega 2 omega. I think
That's an invariant ultrafilter.
so. You have that's in your ultra powers of Boolean algebra
Yeah.
paper.
And I point out that's an invariant of the ultrafilter, right? That cofinality.
Yeah, the cofinality against a decreasing omega sequence, you can program that in your ultrafilter, and you can make, I mean, the cofinality is everywhere the same for this one, and it's say the minimum cofinality that you can have can be omega 2 for one ultrafilter, and it can be omega 1 for another ultrafilter. In fact, you can get every regular between omega 1 and continuum, including both. So if CH fails, there are two distinct I sub U's things. Okay, why is this thick? Well, let me make a slightly bigger picture. If I have a sequence of those cut points that goes down, then the set of those cut points is discrete. So the closure is beta n, is beta omega. Why? Because I sub U is an F space. Because it's a closed subspace of beta H minus H, which happens to be an F space. So now you might think, so what? Well, the nice thing about the structure of those I sub U's is that if you have a sequence like this, and you take the infimum of that sequence, so to speak, then the whole closure of that set, the boundary of that set will have to occur in that infimum layer. So the largest layer below our decreasing omega sequence has to contain all the points in the closure of this sequence. So it has to contain omega star. Omega star sits in there. So that makes it thick because it's as big as omega star is. Well, it's actually way bigger because it's also a continuum. So it's a, if you look at my paper from long ago in one of the Prague recent progress things, I summarized what Eric van Douwen and Muraszewski had done on the structure of these continua. And this is one of the major things. The continuum is what they call irreducible between the top and the bottom point, meaning that it is the smallest. If you take a subcontinuum of this thing that contains the top and the bottom point, it has to contain all the points. And if you look in Kuratowski's topology book, where he does an extensive study of these kind of things, those irreducible continua have a pre-order. You can say that X sits below Y. If X sits in every continuum that contains Y and 0, that is a pre-order. And those thick layers, they are things that are all mutually comparable in that pre-order. If you take an X and a Y in that little blob, then X is less or equal than Y, and Y is less or equal than X. Because the one continuum that contains both of them has to, if the continuum that contains 0 also contains Y, then it has to contain the whole layer. And so then X and Y, like I said, are above each other. So the I sub u looks, it seems to look like an ultra power. It almost seems like it's linearly ordered, but every increasing sequence, every decreasing sequence bumps into a really fat layer. So it's, I don't know, sometimes I think of it as a piece of string with lots of thick beads on it. And between the beads, there are the points that you can see from the string that can act as cut points. But I'm not quite sure how good of a metaphor that is. Anyway, so
Are all
we
the
have-
thick layers homeomorphic to each other?
CH.
Under CHS?
under CH, they're all homeomorphic to H star itself.
Oh, they are.
Yeah.
Is that just the cofinality omega layers, or?
Oh, the cofinality omega layers, they're all H star, and I'm not sure about the other ones. They're indecomposable for sure.
Probably did know once, but just forgot.
Or I thought about it once and stopped and forgot that I ever thought about it. But
While you're pondering it, just let me point out that the cofinality is only from one side, because you can't have two copies of omega stars as such.
again, because of the Fness. Okay, so what is the thing that we're talking about here? Is, well, we have this continuum, we have these cut points, and they're easy to exhibit. You take a sequence in your intervals, take the limit along the ultrafilter, and bang, there's your cut point. And so the big question is, are there any others?
Is that asked by Michelle Smith or just folklore?
I think Michelle Smith and Stuart Baldwin had something under MA countable.
Yeah.
I'm not sure who actually explicitly posed the question, but it sounds like it should come from Auburn in this case.
You have an infinite page.
I don't have an infinite page, and I just realized that I didn't know how to add pages in this program. Now I know. Anyway, so the question was, can we find any other types of cut points in these continua? And like Alan mentioned, Michelle Smith and Stuart Baldwin, they did some work on this. They found, I think, under MA countable, I think they found some U and some X. That's a cut point. And X was even remote. Now, Alan can pontificate on what remote means, but it means, I'll say it anyway, X is not in the closure of F if F is nowhere dense in M. So that sequence that gave us a cut point is definitely nowhere dense. And X is not in the closure of any one of those things. So it's a non-trivial cut point, for sure. And I think, what's his name? Jianping Zhu. He had a partial result. He showed that in the Laver model, that we will talk about this week. In the Laver model, there are no remote cut points, is how you formulate it as there are no simple cut points, but when you look at the definition of simple, it means that they are remote. But that doesn't kill all the non-trivial cut points, because you could still have ones that are in the closure of some nowhere dense set, but not in the closure of those sequences, for example. You could conceive of a cut point that sits inside copies of the Cantor set or something like that. And actually, while we're at it, a non-trivial cut point is a far point. And a far point is one that is not in the closure of a closed discrete subset of M. So you have to work a little bit on that, and I'll get to that in a moment when I'm formulating some criteria for a point to be a cut point at all. So if you are a non-trivial cut point, so then you're not in the closure of any choice sequence for the interval, so to speak. But it's even better or worse, depending on your point of view. You're not even in the closure of any closed discrete subset of M. The reason that you can avoid even closed discrete subsets is that, of course, D intersect every N across the unit interval is finite. Because if you have a closed discrete subset and you intersect it with a compact set, you have to have something finite. And that will allow you to actually avoid those closed discrete sets too, if you are a non-trivial cut point. I'm not saying that a far point is like this. I'm saying that a non-trivial cut point, a far point is a non-trivial cut point, and a non-trivial cut point is far. So I guess that, a far point does not need to be a cut point. It could be in one of those layers, and then it's not a cut point of the continuum. So let's just erase this, not say anything about it. That's one thing. And if we're also working towards how to prove that there is a model without non-trivial cut points, one thing we need to do is find something combinatorial that we can work with and destroy if we want to kill those cut points. And that's the following things. I'm drawing my picture again. Okay, this point X is at this point not necessarily a cut point. It could be sitting inside one of those thick layers, because what I'm writing down makes sense for every point in I sub u. We can look at all the sequences and okay. So what do I mean by this? Okay, so I have a sequence of A's. Here are a sequence of points A. Those points give us these intervals here, of course. And when I take the closure, I take a whole bite out of M star. And if X happens to be in that piece of M star, then I'm saying that, oops, the sequence A belongs to AX. It's A determines a cut point, and that cut point is below X in that order. And BX, well, you can guess what that's going to be. So again, that's cool. Let's take some blue points here. And then we get the blue intervals, we take the closure. And of course, the B's determine a cut point, and I'm looking at the cut points that sit above X. These two things, they form a gap in that ultra power that we talked about. If I take a member of A and I take a member of B, then in the ultra power of the unit interval modulo the ultrafilter U, the sequence A sits below the sequence of B's. And so what was I going to say? Well, X is a trivial cut point. So that means that X is of the form X sub U for some sequence of XNs. If what? Well, that sequence is actually in both of those things. I said gap, but if X happens to be a trivial cut point, then it's not really a gap, because the intersection of the A sets AX and BX is non-empty. There is at least one sequence in it, and actually the intersection consists of all the sequences that are equal to this one modulo the ultrafilter. All the sequences that converge to that X, and that's all X modulo the ultrafilter, those are in the intersection. And if X is not a trivial cut point, well, that's if and only if. Well, not a trivial cut point if and only if the intersection is empty. So if X sits inside one of those layers, the intersection is empty, but if X is a non-trivial cut point, the intersection is empty as well. So just saying the intersection is empty does not give us a cut point. It just tells us we don't have a trivial cut point. But, and here is where the combinatorics ultimately comes in. X is a cut point, trivial or otherwise. For every function from omega to omega, there are a sequence A in AX and a sequence B in BX, such that the ends where this happens the set of ends where the difference Bn minus An is less than 2 to the minus Fn, that has to belong to the ultrafilter. So if you take a sequence that converges to 0, then, and you want X to be, if you want X to be a cut point, then there have to be members of AX and BX that are arbitrarily close to each other. And arbitrarily means below any sequence that converges to 0, but it has to be below their only ultrafilter often, of course. So this is how you recognize a cut point. The A's and the B's in the AX and BX get very, very close together. Slightly modified, and actually, this is what we're going to be using ultimately in the proof. And I copied this from our paper, and I'm not using the power of 2 and everything. For every function from omega to n, and n is omega minus 0, there is a g from omega to omega. Well, gn is less than f of n always. And I'll read this. Okay, this set belongs to X. We also think of X as an ultrafilter of closed sets on M. So, or if you don't like it this way, you can say that X belongs to the closure of this in beta M. So anyway, this thing is a member of the ultrafilter that the ultrafilter of closed sets that determines X. If and only if. If you have this null sequence condition, then you get this this one, the F condition, the function condition, and if you have the function condition, you get the null set condition. And this also can be used to, okay, I'll try and find another page. This can also be used to show that those that a non-trivial cut point is actually a far point, because you can probably see this coming. If D is discrete, and I need this to complete one part of the picture. If D is discrete, then we have a function from omega to n. Pardon?
Did you forget closed?
Well, yeah. of course, I'm only thinking of closed sets here, basically. But yeah, if D is closed discrete, then we have a function with the property that if n comma D and n comma E belong to D, and of course D not equal to E, then say 1 over Fn is less than D minus E. So you take the minimum possible distance between neighboring points of D in every one of those vertical intervals. That's what you call Fn. You can also, I don't know, multiply by 3 to be sure. But it doesn't really help because you have to do 2 steps anyway. Then you take your G, and then that union that I'm talking, I don't know, we should give this a name. Okay, I'm calling this F of G and F. Not very, then the F of G and F, okay, it belongs to X. And it hits, if I take the intersection of F, G, and F with D in one of those individual intervals, then the intersection has at most 1 point. And so then I say, oh, but wait a minute, it was a non-trivial cut point, so it cannot be in the closure of the choice sequence either. So the being a cut point tells you that you can make sure that out of that discrete set, you make a choice function that could possibly converge to the point. But if the point is a non-trivial cut point, that one choice sequence cannot converge either. So it's not in the closure of that discrete set. Why did I mention this? Well, for 2 reasons. 1, because we need it later in the proof. And 2, because I want to sort of complete the picture under CH regarding those cut points. Induction. If D is closed, scattered, of finite rank, so our X is now always a non-trivial cut point. I'm looking at what non-trivial cut points can do. If you take a closed set that is scattered and of finite rank, so could be converging sequences in every in every interval, could be a converging sequence of converging sequences in every interval, but it has to have finite rank, then X is not in the closure of that set still. So a non-trivial cut point walks away from every scattered set, every closed set, scattered set even of finite rank. Like I said, and that's something that is used in the proof of the consistency proof of having no non-trivial cut points. CH, there is a closed set scattered. Okay, let's call the closed set E, scattered of rank omega. And the way we built it is it's a converging sequence in the first interval, it's rank 2 in the second interval, rank 3 in the third interval, and so on, because that's the only thing we need. Such that the closure of E has a non-trivial contains a non-trivial cut point in every I sub u. If you look at it, if you think of it, when you start to do the when you try and build this thing that we have up there, you can do that. You can do that on the scattered set, and when you have the continuum hypothesis in your hands, you can simply get everything to go mod finite, and then you find that you have created a whole vertical line along the whole of M star, consisting of cut points, non-trivial cut points in every one of those I sub u. So this is the minimum size, so to speak, of a set that can actually carry a non-trivial cut point, assuming the continuum hypothesis anyway. I'm not going to prove that, but this here, and let me this here is going to be the secret, the key to proving that in the KPLaver model there are no non-trivial cut points. Let's see where my preparation is going. Yeah, I think I said most of what I wanted to say about the cut points. Well, let's give a nod to the Borel conjecture anyway. And when I was preparing this, I was struck by the similarities of the things that we have to do. So let me talk about those similarities for a moment. The Borel conjecture, what's the Borel conjecture? Well, maybe you've seen this in measure theory if you haven't seen it somewhere else. It comes from Lebesgue measure and all the definitions of Lebesgue measure that you can think of. And what does it mean to have measure zero? And when you look at the definition of Lebesgue measure and you look at the characterization of measure zero, yeah.
Nobody said anything.
Okay, well, there was a noise coming from the room. So when you look at all those definitions, this one seems reasonable. It has strong measure zero if something that you would think should hold for measure zero sets holds in this. If you have a sequence for every sequence, I'm formulating this implication. Okay, really real reals in the real number line. For every sequence of positive real numbers, there is a sequence of intervals. Okay, IN, such that what? Well, the length of IN is at most epsilon n for every n, and X is a subset of the union. This almost looks like the definition of measure zero, except that in the definition of measure zero, you just take one epsilon, and you do want sequences of interval, you want a sequence of intervals, you want it to cover X, but you want the sum of the lengths of the INs to be at most that given epsilon. Here you ask for much more control. You want to be able to say something about the length of every individual interval in the sequence, which is a stronger demand.
I suppose you could also say
Pardon?
that measure. I suppose you could also say measure zero rather than strong measure zero, that the measure of the INs is less than epsilon rather than their length.
Yeah. I think there are versions of this without intervals even. But this is the definition that everybody always mentions. So yeah, I could say where lambda is Lebesgue measure.
Well, I think that would be wrong.
Hmm?
I think that would be wrong. You need length for strong measure zero.
Yeah.
So if you weaken that to measure, then I think you're back to just normal measure zero.
Well, the length of the interval is the measure of the interval. So
And I'm saying don't take intervals. I'm saying don't take intervals. I'm saying take open
Yeah.
sets. Yeah, I was misleading.
anyway, the official definition has intervals and lengths. And lambda means length, by the way. Or it's the initial of Lebesgue. Anyway,
We had another camera set is not this.
you were saying, Will?
I was telling Jacob behind me that it's a good exercise if he hasn't done it to show that the canter set is not this.
Right. Okay. Well, and Borel okay, easy. That's another exercise. A countable set has this property. Every countable subset of the real line has this property. And Borel conjectured that if something has this strong measure zero property, then it should actually be countable. Presumably because he couldn't think of any example that didn't have the property other than countable sets. And presumably because he also checked that the Cantor set didn't have this this property. Okay, I'll take another piece of paper here. Is the Borel conjecture true? Well, no. CH will give you a Lucent set. And that has strong measure zero. And what is a Lucent set? Well, a Lucent set is uncountable. But intersects every lower than set in a countable set only. Named for Lucent because he constructed one. So why is this strong measure zero? Well, you take your sequence of epsilons and you take the even epsilons to cover the rationals with intervals of that particular length. Then you get an open set around the rationals, and the complement is nowhere dense. That has countably many. So apparently, those countably many intervals that you threw around the rationals already pick up almost everything of your Lucent set. You miss countably many points. Well, then you can take the odd numbered epsilons to cover those, and there you have it. And in the 20s, Sierpinski and other Poles, they did all kinds of tricks to find strong measure zero sets and universal measure zero sets. There is a whole collection of notions of measure zero and smallness that they were looking at. But it took until the 70s to show that the Borel conjecture is actually consistent. And that is what Lever did in the 1970s. The paper appeared in 77, apparently. Yeah. He proved the consistency of the Borel conjecture.
You know the journal? Is it Annals or
Pardon?
do you know the journal?
Acta Mathematica. So it was deemed important enough for that journal. Yeah.
So
Okay.
I think it's important enough for that.
Well, it also has the, I think, Stevo and his wild coloring of omega-1 squared and the row functions and such. Okay, so one of the things I wanted to point out was sort of a parallel between here, where was it? Here is our Yangping Zhu also had a condition like this. This condition here in the red rectangle, it tells you what a non-trivial cut point should do. And the thing that I'm going to write down here, which I stole from Baumgartner in a paper that he wrote in 78, 77, something like that. There is a book, small book, with surveys in set theory. And I have it. And that's there is one of the first survey papers about iterated forcing, and Baumgartner proves the Borel conjecture in the Matthias model. Because the proof is almost the same. And in that, Lever actually worked in the ordinary real line when he was proving that the Borel conjecture held in his model. So he was looking at real intervals and midpoints thereof, and he needed all stuff like that. Baumgartner translated it into something. So Baumgartner's translation. Baumgartner's translation is as follows. He doesn't do the real line. He works in the Cantor set. In the guise of the sequences of zeros and ones. So not the middle third set, but the product of all the infinite 0 and 1 sequences. And of course, if S is a finite sequence of zeros and ones, then we write this as all the points that extend it. So this is a basic Klopen set in the Cantor set. And we say that it has as a set of ordered pairs, it has a cardinality, and that cardinality, the negative 2 power of that is what we deem to be the measure of that Klopen set. And that gives a measure on that Cantor set, and you can translate by the normal mapping of the Cantor set onto the unit interval, then this measure gets simply transformed into the normal Lebesgue measure on the unit interval. So whether you prove the Borel conjecture for the whole real line, for the unit interval, or for the Cantor set in this situation, that's basically the same thing. And instead of intervals, we're looking at those basic open sets. And X, a subset of the Cantor set, has strong measure 0 if what happens? Well, and like I said, this was sort of the striking similarity. For every f from omega to omega, there is a g from omega to, well, not omega, but to the finite, to the tree of finite sequences of zeros and ones, with Gn is a sequence of length Fn. So every Gn picks out one sequence of length Fn. That's one thing. And that sequence, of course, the terms of the sequence determine Klopen subsets of the Cantor set. Well, these Klopen sets play the role of the intervals that we're looking for. And so X is a subset of the union of those basic Klopen sets, where we specify the measure of those basic Klopen sets. We want them to be have measure 2 to the minus f of n. And so the Borel conjecture states in these terms, every uncountable subset of, for every uncountable subset of the Cantor set, there should be a function where this fails, because we don't want any uncountable set to have strong measure 0. So what do we have to do if we want to prove the Borel conjecture, or we want to prove that there are no non-trivial cut points in the Laver model? We should prove if X is a far point, in M star, then there is a function f from omega to n, such that for no g to from omega to omega, does that, what did I call it, this set f gf belong to X? So we want a function f where the thing that I had in the red box fails. So that means that for no function g, that set that I wrote there belongs to the ultrafilter, the closed ultrafilter X. That's the thing that we need to prove if we want to kill all the non-trivial ultrafilters. And apparently, if X is uncountable in the Cantor set, then we don't want it to have strong measure 0. Then there is an f from omega to omega, such that oops.
Cardelli.
So for no function that picks a clopin set of measure 2 to the minus fn, can we, with no function like that, can we cover the set X? I thought it was nice that we have to find, apparently, in both cases, we have to find a function from omega to omega. Okay, fine, from omega to n or from omega to omega, that's the same thing. Such that for no function g, and of course here we need that g of n is less than f of n, because that's what we needed to make those intervals. Does that set f g of f belong to X? So, okay, here is the nod to the Borel conjecture, in the sense that there are two very similar statements that need to be proven in that final model. Well, I'm not going to get to that type of argument today, but I want to indicate where that function is coming from, and then we'll do most of that on Thursday.
Ask real fast. So you mentioned that the Borel conjecture holds in the Matthias model as well.
Yes.
Does your theorem with the cutpoints also hold in the Matthias model?
Can you look across the table and see if there's a nod or a...
I would venture yes.
Yeah.
Yeah.
So,
Okay, now I dare to venture yes too.
okay.
So you haven't proved it,
No,
but I'm sure.
I was looking at the Baumgartner paper, and it seemed basically to be the same thing happening there as in our paper. And the I think the real main property that we'll be using, and I'll talk a bit more about that on Thursday, holds for both forcings. The crucial thing, that what we need, as you can guess, is that we need to give a function. Well, where that function comes from, I will tell you in a moment. And then we need to keep those g's under control. So we have the function, and then somebody gives us a g with property that either it belongs to that set of finite sequences, or it's simply smaller than f everywhere. And we need to get a handle on those g's. And the handle that the Lever forcing gives us is basically the same as the handle that the Matthias forcing gives us.
Yeah, the labor property.
Yeah. The Lever property is like the sex property, but with an extra condition. If you have a, okay, I'll mention what the Lever property says. If you have a function that is bounded by a sequence of finite sets from the ground model, well, no, sorry. Yeah, you have a sequence. In the first case, we have a sequence of finite sets given by the fn's, simply the fn's themselves. In the other case, we have a sequence of finite sets, namely the sequences of length fn. And the Lever property tells you that you can capture such a function by a ground model sequence of finite sets where you can specify the size. So you can say, I want the first set to have 1 point where I capture G1 or G0, depending on your point of view. And G2, I want to capture it with 2 points at most. And G3, I want to be it among those 3 points. And G4, I want it to be among those 4 points. So you can really, really restrict the possibilities for that function, as long as that function is bounded by something from your ground model, so to speak. And that is that Laver thing, and that will occupy us on Thursday a bit more. So yeah, so here is how the story will unfold, but most of the unfolding will happen on Thursday. Where does the function come from? Because I'm saying there is a function. Where does it come from? We need one. Where is the f coming from? Well, what is the Laver model? We have a partial order L, and I'm not going to describe it just yet because, well, for what I'm saying, we don't really need it because the properties that we'll need of it, I'll talk about later. L, the Laver partial order, iterate it omega 2 times, countable support, okay, fine. That is all fairly standard. So you get a sequence of partial orders, P0, P alpha, and in the end, we have our P omega 2.
Invented in Laver's paper.
Pardon?
Standard and invented in Laver's paper.
Yeah. And there is a reason for that. If you do finite support, all those Cohen reals will resuscitate those uncountable sets. They'll give them strong measure 0 again.
Not to mention, you'll keep collapsing the continuum. We've used Laver.
Other than that.
Collapse. Cosmic.
Oh, you'll collapse and make a one? No, it's still be.
We can't do Laver flags. Anyway, go on.
Yeah, but
Oh, no, you're right. This class is
Yeah, I think you're right.
But anyway, one of the things that Laver mentions in his paper that he said that if you do finite support, you'll get Cohen reals, and the Cohen reals will resuscitate those strong measure 0 sets anyway. You know, they're dead, and they'll be raised from the dead by the Cohen reals. And that was one of his reasons why he did countable support, apparently. But also,
the Cohen reel adds a sequence of
Intervals that covers it.
yeah. Okay, so what's the idea in both proofs? Well, suppose you have a far point in the final extension. So we take the generic filter on the whole big thing and we call it G omega 2, or we have X uncountable. In that final extension. Well, those things have names. So we have names for those things, and we do the dot thing. That
Suppose you want X size omega 1.
Pardon?
Suppose you want capital X size omega 1.
Yeah, without, of course. We only need to show that LF1 sized sets are not strong measure 0, then the rest will follow.
Yeah.
So X is size omega 1, X, the little x is a far point. And then what? Well, they have names, and you can write down what it means to be a far point in beta M. That's a few quantifiers. And you can use a closing off argument or an elementary substructure argument or whatever you want to find an alpha such that if you take that name and you restrict everything in it, what you use in it, to alpha, then you can make sure that a reflection of that far point in the final model is already far in an intermediate model. And because X has size omega 1, there are actually club many alphas with this particular property. We can also make sure that X is simply an element of VG alpha. X is a set of omega 1 many reals. Every real appears along the way, and after aleph 1 many alphas, you have all the members of X. So we know that we can have an intermediate model where we have, say, X restricted to alpha. That's our far point. And our future uncountable sets is already there. Okay, size aleph 1. And V of G alpha satisfies the continuum hypothesis still. That is one of the things that Laver also proved in his paper. And the rest of the iteration is just the iteration performed in V of G alpha. So we restrict G to the first alpha partial order, we take that model, and then the rest of the iteration is actually, well, is isomorphic to the iteration as we would have performed it in V of G alpha. In 1977, this was big news. Right now, it's part of every course enforcing that tails of iterations are iterations in the intermediate model and whatnot. But both Laver and also Baumgartner in his survey very explicitly said, yes, we can just pretend that we are doing the iteration starting from the intermediate model if need be. So without loss of generality, X and X are just in our ground model V. So, but we have to keep in mind that, okay, the uncountable set X is one that we have to show it doesn't have strong measure 0 in the very final model. Our point X is a shadow
of its future self.
All right. Go to your room.
Todd's signing out now.
Is a shadow of its future self. So what is going to happen? So what are we going to try and do? Okay, so the future self doesn't want this FG of F to be a member of it. Well, we simply make sure that for the X, what we're going to do is we're going to show that if you take a G or a name for a G eventually, then we're going to find simply a subset F in the ground model that belongs to the shadow that is already disjoint from that F G of F thing. So that means that the future self can never have one of those FGFs as a member. So that's the one thing that we're going to do. And For the X, okay, I still haven't told you what that F is, but I'm going to tell you in a moment when I've told you what the Leverpo set is. We're going to force that X is not in the union of those GNs. Okay, so now what is the F? Now, what is the Lever forcing? Well, it is all the subsets of this, it's the family of all the subtrees of the tree of finite sequences of natural numbers, such that it looks like this. There is an element ST in that tree, here it is, such that if you have any other element in the tree, then it's an initial segment of ST, or ST is an initial segment of it. So below S of T, it really looks like the stem of a tree. And after ST, it's going to branch out. And it's going to branch out really terribly densely. And this is the best interpretation of a Lever tree that I can give you. If T is in T and S of T is an initial segment, then the set of n's such that T concatenated with n belongs to the tree is infinite. So it's a very, very, very bushy tree. S of T has infinitely many direct successors. Every one of those infinitely many direct successors has infinitely many direct successors. Okay, and you get the idea. All the way to the top, we have these very thick, tiny brushes sprouting out of the points in the tree. That's the set. Okay, maybe I should close the curly braces here somewhere. The order is just, inclusion, reverse inclusion. S is stronger than T means that S is a superset of T.
The other way around.
Hmm?
Other way around. Or are you switching to Shala?
You're right. I'm not switching to Shala. There you go. It just means that it's a subset. And if you have a tree, then we extend that notation of the square brackets in a moment. Those are all the x's in omega to the omega, such that for every n, it's the set of all the branches that go through the tree. That's a closed subset of the bare space. And if G is generic on L, then, well, we can do two things. We can say F is the union of all the STs where T is in G. Or we can say that the intersection of all those closed sets is non-empty. It consists of exactly one point, and that one point you can get by taking the union of all the stems of the trees. Because the thing is a generic filter, all those stems of those trees have to be comparable, and their union therefore is a branch. And it's a branch in every one of those trees. And this is the F. Well, to be precise, we have our model, we have our ground model V, we have our X, which is a far point and also a shadow of its future self. We have a capital X, which is an uncountable set, which we want to show that is not strong measure zero. We needed a function F. Well, that function F comes from the very first Laver partial order in the iteration. The first partial order gives us this function. This function, I'll leave it to you to check, is very fast growing in omega to the omega. Because if you have an it's a dominating real. Because if you have a ground model function, at every level, you just cut away the finitely many branches that have values below your function, and that shows you that the generic function is above your given function, not finite. That function F, the one at the very beginning, is the one that does the trick both for the far point and for the uncountable set. So the rest of the proof, and I hope to give you a sketch of that on Thursday, we're getting near, I guess, the end and everybody's falling asleep. The rest of the proof is devoted to showing that any other function that we might encounter in the final Laver model, and the function is bounded either by F itself or by 2 to the F, cannot make our X a trivial cut point, a non-trivial cut point, or it cannot help in covering that uncountable set that we're talking about. So the things that we need to do is, well, we need to find an F. Well, here it is. The first Laver post set gives us the F. Then it's up to the rest of the iteration to show that nothing strange happens underway that will either make the uncountable set strong measure zero anyway, or will have a future self of our far point that happens to be a non-trivial cut point. We want both of the things not to happen. And that is where the Laver property in its full force comes in. And for the cut points, we do need at one point that I think scattered sets of height 2 or 3 are also staying away from that far point that I was talking about. So yeah, I think that is what I wanted to say today, and I hope I left you wanting more.
Let me add to your list.
Pardon?
Let me add to your list for Thursday. You could show us that there can be a far point which sits in the layer. I think that could be interesting.
Pardon?
That there can be a far point that sits in a layer. I think that's counterintuitive. I think that's where
Okay.
Mark do it. And
Yeah.
maybe I don't know, no rapid ultrafilters, but maybe that's too much.
We'll see. But the getting a discrete set to converge to a layer, yeah, that sounds good.
Yeah. Well, thank you.
Yeah, thank you.
Now you have to clap.
What?
Oh, hi, Todd, you've appeared.
Yes. All set for next Tuesday, Todd, eh?
I hope so.
Looking
Now I'm
forward to
not
it.
scared.
Now what?
Now I'm not scared. I'm following KP, so I can do whatever I want. I look good, right?
It will be a shadow of his future self.
Yeah, that one. I could smell that one here.
I'll bet more like I took the words right out of your mouth.
There was known as L. Dow Richard.
All right, well, let's all reconvene on Thursday. What's the temperature where you are, Todd?
Getting near 100 tomorrow, so
Yeah, we're
How much is that in real money?
36 or so.
Right.
Yeah, I think 38.
well,
We had some,
I see.
we had some really big storms come through last night, take down trees around, so
Oh. So you're alone with the kids? Jerry's up
No.
in Toronto?
she's back.
Oh,
Although she's working in a physics lab for fun this summer, so we'll,
she knows how to have fun just like you do.
yeah, I'm afraid so. So I've been watching the kids during the day.
Well, we had a balmy 18 degrees right now. So-
Oh, you good.
And you can convert that to whatever it is that you're using up there. But,
Comfortable.
63 and a half.
Kelvin, speaking of Kelvin.
Yeah.
what, you're not using the Réaumur scale anymore?
60 Kelvin, that's like the temperature of Ganymede or something. All right, I'll see you folks on Thursday.
Yeah.
Okay, see ya.
Yeah.
See you, Kevin.
All right.
Okay, cheers.
Cheers.
You recorded this, didn't you?
Yeah.
Okay.